So, okay, good afternoon, everybody. Today we are going to finish this this second chapter of our course, which is quantization of charge, light, and energy. Last time we overviewed the quantization of charge, the measurement, the discovery of the electron through the study of what they used to call, we still call it like that, which is cathode rays, which are rays of electrons. And so by studying the behavior of these rays, they characterized, first Thomson measured the ratio of the charge of these particles over their mass, and a few years later, Millikan measured the charge and so independently the mass of these particles, and so now we call them electrons, and their charge is what we call the elementary charge, and this is now how call it? This is the value is exact. This is an exact value, okay? And so what we are going to see today is the quantization, okay? Another kind of quantization that was really very, very important for this modern science, the modern physics. This is the quantization of light and energy, okay? So we already began quantization of electric charge. Blackbody radiation. This is the problem that seems to have initiated the modern physics. Actually, we will see that photoelectric effects also was something that were being observed and studied before Planck and Einstein described them. But let's begin with the blackbody radiation. Okay. So, okay. We still have this one. This is the okay. Quantization of charge, the measurement of Q over M. Okay, cathode ray, and Millikan, the measurement of E, the elementary charge, and of M, the mass of electrons. Okay. And now, so we will study a little what is this problem of the blackbody radiation. Okay, this is actually what we call thermal radiation. Okay. So let me write it here. This is thermal radiation. Okay. So this is something that can be observed. Okay, you have first opaque. I don't know how to pronunciate it actually. These are bodies. Okay, this is opposite of transparent. Okay, so a transparent body is some material that let the light, okay, propagate, okay, pass through it essentially without absorption, okay. So yeah, you have other effects. Particularly, you can have some, okay, you can think of visible light, and you can see effect when you pass a ray, okay, of visible light through at the interface between air and glass, for example, or water. And we can say that glass, particularly, some kinds of glass are quite transparent. Okay, some of them don't absorb. Okay, in the laboratory we have special glasses which don't absorb, and so you can observe the refraction and reflection of light, but this is still a transparent body because it doesn't absorb. Okay, so an opaque body is some material that absorbs and emits light. So when it absorbs light, so you have light incident on your material. Okay, so you can think of some material. Okay, and so you have light. Okay, I will put it for now. We think light is a wave. Okay, an electromagnetic wave, and so you have light illuminating this material, and this light will interact with the charges and the constituents, okay, atoms and of the material, and so they will put, for example, the electrons, okay, to this is an electric field, okay, an electromagnetic wave. There is an electric field, and this electric field incident on the material will put the charges to oscillate, okay, at a certain frequency of the light. And when you have, okay, so we can write it this way: light, electromagnetic wave. Okay, this is light incident on material. Okay, so it puts oscillating charges. Okay, and so these charges, so first this is absorbed, okay, by the material, and so absorption will be used to oscillate, okay, the charges inside the material. And so you remember from kinetic theory of gas, for example, but it's you can use it also for solid materials. When you have the oscillation, okay, of the atoms, okay, for example, so you will have, this is related to the temperature, so higher amplitude of oscillation will lead to an increase of the temperature of the body, okay, and so you have increase of temperature, okay, of the body due to this interaction. But on the other hand, you have also a decrease of temperature. Okay, this is oscillation of particles. Okay, and what will lead to decrease of temperature is the fact that you have oscillating charges. I don't know if all of you have had this course on electromagnetism, okay, and you can you study in electromagnetism that oscillating charges, not actually accelerated charges, okay, accelerated charges. What do they do? Accelerated charges. Do you remember? They emit light. Okay. They emit radiation. Actually, they emit electromagnetic waves. Okay. So light, I will use it more for visible light. Okay. So they emit, depending on, okay, the particle, the acceleration, they emit electromagnetic waves. And so when you know the wave, electromagnetic wave transport energy, and so this will lead to a decrease, okay, of the energy available for the particles, and so this will lead to a decrease of the temperature. And somehow you will have, when you have competition between two opposite, okay, effects, you will have some equilibrium, okay? So you will have an equilibrium temperature, and particularly you will have an equilibrium between the absorption, okay, of light, of electromagnetic waves, and emission, okay, of electromagnetic waves, okay? So a good absorber, for example, is also a good emitter, okay? Because due to this, the fact that you need to, we are studying equilibrium, okay? Black bodies. And so you have an ideal black body. So this is a black body, okay? Why do we call it black? It is because black absorbs, okay? If you have some white surface, the white surface will essentially reflect, okay? The light, the black surface will absorb the light, okay? So what we call an ideal black body, it absorbs all light. It's a perfect absorber, okay? All incident light, okay? And so it also emits, okay, a lot. It absorbs everything and emits in the same proportion, okay? All incident light. So this is an ideal black body. So why is it important? Because this is something you can observe, okay? For example, you can see that at room temperature, you don't observe, okay, this emission of radiation, okay, because we will see it is essentially in the infrared, okay, range of the electromagnetic spectrum. But as when you increase the temperature of these black bodies, okay, any material actually, so when you increase the temperature, you will observe the color, okay, changing, and it changes from some color, okay, you can to it glows, okay, it glows. First it is reddish, after that it is frankly red, and if you increase a lot, okay, the temperature, you will have something which is white, okay, and white, you know, it's not a color, it is, you have all the colors. And so the colors of the materials, they change depending on their temperature. So this is very important, because first is if you see it is observed, you have to explain it, okay? Physicists can't live if there is something like that happening and they are not able to explain it. And also there was and there still is a real necessity of measuring the temperature of a body. Okay, for example, in the oven, how you call it, in the industrial revolution, okay, so you put some iron, okay, in an oven and you see its color changing, and you cannot put some obvious thermometer to know the temperature, because the temperatures are very high. So you would like to, as you see that the color is related to the temperature, so you would like to have some thermometer based on the color of the material, okay? The thermometer, I remember you, this is something that measures the temperature, and it uses for that any phenomenon, okay, that depends on temperature. So you can have dilatation of things, okay, metal, or you have mercury, for example, or alcohol. You can use the resistance of, okay, in electronic circuits, you can use the resistance, you can use a lot of things. And so you can use also the color, okay, to measure the temperature. And so this was very important. And what was the problem? So it was at the beginning very empirical, okay? And so the first law was the Stefan Boltzmann law, okay? So first, Joseph Stefan, he observed, he measured, okay, what he called, okay, so I will write, okay, what is this law? Stefan Boltzmann, because Stefan, I think he wrote the law quite empirically, phenomenologically, he measured, okay, and Boltzmann probably found this law using the laws of thermodynamics, okay, and things like that. He was a specialist, okay. So what you have here is a quantity, okay. So what can you measure, okay? Imagine you are an experimentalist or someone who wants to measure something, and so you have some material at a given temperature, and so you measure the light, okay, so you can put a detector, something, okay, which will measure, and so you will measure essentially, for example, the energy, okay. So R is this energy. So let me check here the exact nomenclature, okay. So this is the power per unit area. Power per unit area, okay, we sometimes call it intensity, okay. Power per unit area, okay. So this is watt per meter square, okay. So you have something to measure power, okay, and you want to relate this value, okay, actually this is the total power, okay, as a function of the temperature, okay. So you have something at a given temperature T, and it is also for ideal, okay, ideal Blackbody, okay. So this is a Blackbody, really, and so he found that he had really a relationship between these two quantities, and this was R is proportional to T at the power 4. Okay, so this is a very strong dependency, okay, on temperature, and there is a coefficient, a constant here, and this is called Stefan constant, okay. So you measure experimentally, so you can imagine, okay, how can you do that experimentally? You measure first, what is your variable? You have here the temperature, and so you measure the power, okay, here, or as a function of temperature, okay. And so you observe, okay, this behavior, and this is something very, very, very strong, okay. So this will be very qualitative, okay. Depending on the scales here, this can be any power, okay, any coefficient here, and so he had some experimental points, okay, measured, and obviously what is the unit here of T, okay. If you have something, it has to be Kelvin, okay. It cannot be Celsius, okay. And so you have some experimental points, and you try to pass some, okay, to verify some mathematical relationship, okay. And this is quite simple, this one, okay. And so measuring this, you can determine the value of Stefan's constant, and I will write it here. Sigma is 5.6703 10 to the minus 8, and the unit is, okay, here you have watt per square centimeter per square meter, okay, per Kelvin at power 4. Okay, so this will be watt. Okay, and so this is measured. This is experimentally measured. Okay, and Boltzmann also obtained, okay, this relationship. So this is a constant, okay, it doesn't depend on temperature. So you see that this total power only depends on temperature for ideal black body, okay? If the body is not, the black body, okay, the emitting body is not ideal, so it will depend on other not ideal black body, and R depends, is a function of temperature, of course, and also other, okay, other parameters, okay. So this is for ideal black body, okay. And so also, if you have something that is not black, you have some mitigating factor. We call it emissivity, okay. And it's always less or equal to 1, okay? 1 equal 1, this is the ideal, okay? Less than 1, this is not ideal, okay? And so you will have this yeah, I guess R epsilon sigma, okay? Okay, so this is very interesting, but there is something else you can, we say that you have the energy as a function of temperature, but before that we said that we can observe, okay, a dependency between the temperature and the color, okay? So what is the color? The color is the frequency of the light, okay, emitted light, and the frequency or the wavelength, okay? So we would like to have something discriminated as a function of the wavelength. Let me see here. I will put a new page here. Okay, so I would like to measure R, okay, the power, okay, but this time as a function of the wavelength, okay. So what is this one? This will be the power, okay, per unit area, yeah, emitted between wavelength lambda and lambda plus T lambda, okay? So to measure this one, you need some experiment that will discriminate, okay, between the wavelengths. So this is something we are going to see later, okay, when we will see the spectrum of absorption or emission spectrum, okay. For example, when we will study the structure, the atomic structure, okay. And so I don't know if I have here, no. We have, so you have your, okay, emission, okay, something emitting light, and at that time, okay, so you have light, and so you will put some something, okay, here you will select a direction, and you will put some prism, okay, some dispersive element, okay, it can be a prism, okay, and this dispersive element actually will depend on the wavelength range, okay. prism we use for example, in the lab. I don't know, some of you have worked in our lab, so we have prisms, we have diffraction grating, okay? So this is something that will spatially separate, okay, spatially separate, spatial separation, actually, spatial separation as a function of the wavelength, okay? So you put some prism, let me see here, so that I don't okay, I can put here a prism. Okay, I will. Okay, a prism is something like that. Okay, so you have the light. Okay, all wavelengths. Okay, let's say you have a continuum. This is very important, actually. The emission of light by the thermal emission of light, this is a continuum of radiation, okay? So next, when we will begin studying the atomic structure, we will see that atoms, okay, and molecules and everything, they have discrete, okay, spectra of emission or absorption. This is not discrete. You don't have lines, okay? You have a continuum of wavelengths, okay, emitted here. So you have your wavelengths here, and so you will have refraction here, and you will have, okay, it will separate, okay, the wavelength. And so what you can do here, you can put some film, okay, some sensitive film, okay, that will show you, okay, what are the wavelengths emitted. Actually, as we have a continuum, it's not very interesting, okay. It's better to put some detector, okay. So at this place you put a detector, a power detector, okay, power detector, detection detector, okay. And so you know that you have to calibrate first, of course. And so you know that there is some, for example, some axis here. I can call it X, okay? So you know that X actually has a unique, okay, relation to the wavelength, okay? And so depending on the position, okay, of your detector here, you know that you are detecting the power at a given wavelength, okay? And so, okay, this is what we are interested in, because we want to have a relationship between the color, the wavelength, and the temperature, okay? So we will, I already can show you the result, okay? So this is the result. And so you have here, okay, the spectral, okay, R as a function of the wavelength, okay, is called the spectral power, spectral power, I imagine. I forgot to annotate this. Spectral distribution function, okay, actually, okay, spectral distribution function, okay. And so, for example, you see you have here on the x-axis, you have the wavelength, here it's nanometer. This is, there is no, this is a normalized, yeah, this is, okay. So this is normalized, okay? This is a spectral distribution function. And so if you have, for example, this one, the big one, is at 6,000 Kelvin, okay? So if you integrate, okay, if you integrate the whole curve here, you should have integral from minus plus or lambda should be equal here to, if it's a distribution, really maybe it's 1, okay? Because we could have a constant. I have to verify this. There is no unit here, and this is the spectral distribution function, okay? So what we had before, so this integral, okay, increases with the fourth power of t. So you can see here you have 3,000 Kelvin, and here you have only doubled, okay? The temperature, 3,000, here 6,000. You doubled the power, but you can see that the integral, which is the total, okay, power emitted, okay, per unit area, okay? So it's much more than times 2, okay? So you have this power 4, which is very important, okay? So the area below the curve, okay, should, if you measure it, it should vary as the fourth power of the temperature, okay? So this is the first thing, okay? So you see 3,000, 4,000, 5,000, 6,000. So the other thing that you are observing, I hope, okay, is that this curve comes from 0, okay, for very, very small wavelengths, okay? You have no emission, it increases, it has a maximum at a value of lambda, which we call lambda subscript m, okay? And this lambda m is a function of the temperature, okay? You see that here it has a value, okay, for this temperature of 3,000. Oh, 3,000 is this one, okay? So really this is much more. You have a value, and as you increase the temperature, it will decrease this value of lambda m, okay? So this is the first observation, lambda m. And you can measure it. It's not only a variation, it is directly proportional to 1 over t, okay? And so here we have, for, it's a zoom, okay? Here for lower temperature, 1,000 Kelvin, 1,500 Kelvin, 2,000 Kelvin, okay? And so you can see here, okay, it's here to show that below, okay, so for a given temperature, okay, here, I don't know, it's here, for a given temperature below a threshold wavelength, okay, you have no emission, okay? So this is very empirical. Now the physicists, they want to find okay, this relationship. For now we only have this one, okay? The power as a function of the temperature. What we want is R of lambda as a function of temperature, okay? And we have the experimental measurements, okay? So Rayleigh-Jeans equation, okay? So this is the name of two scientists, Rayleigh, I suppose it's Lord Rayleigh, and Jeans, okay? And so they found some, they tried, okay, to find an explanation, okay, based on classical physics, okay? And of course, it didn't work, okay, based on classical physics. So what is the the reasoning here. You have some. Okay, I will show you how we model. Okay, modeling of an ideal. Okay, Blackbody. So any material, okay, which is opaque to light, you can use it as it emits radiation, but to use it as an ideal black body, you have some black structures, some black surfaces that can be used, okay? But the best model is the following. You have a cavity, okay? Imagine you have a closed cavity. It's not a sphere, okay? This is a cavity, okay? Let me put here, you have cavity. It doesn't depend on the shape of the cavity, okay? And so you have some very small here, okay, hole in this cavity. And what happens, and so this is an empty cavity, okay, so you have some material here. And here this is empty. And so you will have light, okay, incident on this cavity. And part of this light will be absorbed, okay, actually will enter the cavity, and it will be absorbed by the walls of the cavity, okay. So you have absorption of light by the walls, okay, of the cavity. And so you will have this effect I already explained, okay, that the energy, okay, transported by the light will be used by the material, okay, to heat up, okay, and you will have also, okay, this interaction between the light and the electrons, and so they will re-emit, okay, they will emit light, and so what will happen, you will have light, okay, being, okay, and so sometimes, okay, it will go back, okay, outside the cavity, and so what you do then, you put some detector, okay, and obviously you put a detector, okay, so you put your experiment, okay, with the prism or the diffraction grating, okay, to detect not only the power, okay, getting out of the black body, but also its wavelength, okay. And so this is how you can also you will measure this one, okay. And so this model is good because you can try to physically relate, okay, what happens inside the cavity to what happens outside, meaning what you measure here. So you can think here of, okay, the atoms, okay, of, I will call wall particles, okay, it can be, okay, wall particles, wall, I think the word is not exactly, wall particles, okay, absorb light, okay, oscillate, and emit light, okay, oscillate. So what is the frequency of oscillation? I will put here nu, okay, at the frequency nu, okay, they emit light. And what is important, and what maybe you already studied in electromagnetism, is that at same frequency, okay, the light emitted has the same frequency as the oscillation, okay, same frequency nu. Okay, so so you have nu. Okay, you know nu times wavelength equal. Okay, here this is vacuum. Okay, this is C. Okay, the relation is this one. So the speed of velocity, the speed of light. Okay, in vacuum or R. Okay, it's not very different. Okay, and so we can use lambda as well. Okay, so what will decide, okay, the distribution of energy? Okay, what we are looking for is a distribution of energy. Okay, this is energy per unit area, but this is energy as a function of lambda. So you will have modes. Okay, modes of oscillation in the cavity. I won't go into the details to show you how we calculate. Now, actually, we are interested in the number of these modes, okay? And so, for example, in 1D, okay, you can show if you have something in 1D, one dimension, okay? Let's say you have a wave, okay? It's a rope, for example, an elastic rope, okay? So no, you know you have modes of oscillation, yes? You have the fundamental mode, okay? You have the first, okay, you have this is the first harmonic, you have the second harmonic, you have the third, etc. So you have a number of modes that can oscillate in the cavity. And why that? Why is that? Why don't you have a continuum? Okay, it is because here, okay, it has to be, the electric field has to be the tangential component has to be zero. Okay, according to the electromagnetic theory of light or any wave. Okay, electromagnetic wave. Okay, so you have a number of oscillation of modes oscillating in the cavity. Okay, and so you want to calculate for a given wavelength. So you see it depends on the wavelength. Okay, and so let me take here n of lambda. Okay, so we calculated, okay, that n of lambda was 8. This is n of lambda. 8 times pi. Okay, I can write it. Okay, find the demonstration. And this is a function of lambda. Okay, to the power lambda to the power minus 4. Okay, so you have the number. What is this? Is the number of modes with frequency wavelength. Lambda oscillating in the cavity. Okay, and so what do you need beyond this number of modes oscillating? Okay, you need as you are measuring, this is a number, okay, so it has no unit. What you are measuring here is an energy, okay? So you want to measure the energy, okay, transported by these modes. And so you can calculate times it, okay, almost 5, okay. You will calculate the average energy of this mode, okay. Okay, and so I can call it E, okay, and so n of lambda times this one will be equal to well, this will be only the energy of, yeah, okay. Energy. Okay, first, before going on, I will write something which is R, okay, is a function of the energy U, okay, which is inside the cavity. R is what you measure outside, okay, and it is proportional to the energy, okay, of the modes which are inside the cavity, okay, and we can okay, so this proportionality is C over 4, okay, U, and it's independent of the shape, okay, of the volume of the shape of the cavity. Okay, so this constant, if I remember well, it's not very difficult to find how you can find this constant, okay? So this is it, okay? So you have R proportional to this, probably this is an energy, okay, per unit of volume. Okay, this is what per square meter, and this one should be, okay, you can see with the dimension here you have, okay, so you will have what, which is the no, actually no, this is not what, this is energy, okay, this is joule. So you already have this, and so this is joule, okay, per, okay, so this is the energy density, okay, and this is obviously, as it is a density, it's independent of the volume. Okay. Okay, and once we have that, religions. I didn't write it here. I will. So in the same, we will have for any R of lambda 1/4 C U of lambda. Okay, so now we have the energy, okay, the mean energy at a given wavelength. Okay, so you have, so this is what we wanted. Okay, mu of lambda equal, okay, the number of modes at this wavelength, okay, times the mean energy of these modes. Okay. Okay, and so we can show that. I have something. Okay, so to measure the average energy, the mean energy of these modes, okay, with classical, okay, A, okay, classical, okay, what you do is to define an average, okay, what you do, a mean value, okay, so you have a distribution f of E, okay, okay, some modes will have some frequency, okay, and it will depend on temperature, and you can show that it is always, okay, this kind of thermal, okay, description you make of here this is emission, okay, this is proportional to exponential of minus, okay, so you have the energy, okay, and you compare it, okay, with the thermal energy KT. I will write KB. No, here we are not using K for electromagnetic waves, so K is Boltzmann constant. Boltzmann constant. Okay. Remember K equal, I think it's 1.38. I have to 10 to the minus, just a second, units. Here, Boltzmann constant. Yeah, 1.38, 10 to the minus 23. So this is an energy, okay, so you have Joule per Kelvin, okay. And so here you have some constant, okay. Okay, so when you have this expression, what you do is, when you want to calculate the mean value, okay, so this is something you will, I hope you already used it a lot, and I hope you will still use it a lot, okay. So you have to write it as, okay, you have this distribution function, okay, you multiply E, okay, and so what is your D here, okay, from 0 to, okay, and so you will find this is this constant here. When you integrate, okay, you have to find. It has an energy. It's not finite. It should be sorry, EA minus E over KT dE, okay, and you find this is KT, okay. So this is the classical result, okay, and okay, so I can use it here. So what is the Rayleigh-Jeans equation? You want to have this is what you measure. Oh yeah, I can write it here as U, okay, U of lambda, okay, equal to the number of, I already wrote the number, 8p, okay, times Kate, okay. And so here we have, okay, so you remember that the R of lambda will be equal to, is proportional to that, okay, so you have C over 4, okay, U of lambda. And so you have the same kind of curve, and what you see here is that when T goes, not T, okay, this is lambda, okay, you have U as a function of lambda. So when lambda goes to 0, okay, small lambda, high frequencies, it doesn't work, okay. Well, I won't look here. You have, okay, this tends to, I will write it, tends to, okay, it diverges it, 8 pi over lambda at the 2 power 4, okay. And when lambda, I will put plus infinity, okay, so it goes to 0, okay. So this is okay. Here we can say that for high wavelength, okay, so small frequencies, okay. So if you remember in the visible spectrum, okay, if you put a scale here in wavelength, okay, the visible one, okay, so you have the small wavelength, which is 400 is not, okay, 450, okay, nanometers. And here you have the big, the high, the wavelength, okay, approximately, okay. So this is violet, okay. So here you have ultraviolet, okay, you don't see it, and here you have infrared, okay, for wavelength higher than typically 700, okay, nanometers, and for wavelengths smaller than 500, okay, nanometers, you have UV. So this works for these high frequencies, okay. At least the behavior is okay, okay. But for the small wavelength, okay, high frequencies, okay, I can write it here. Frequency nu, okay, for example, 10 to the 4 hertz, okay. So you have something here. I can calculate. I don't know exactly, but you have frequency increasing this way, and so this is frequency increasing this way. It doesn't work, and this is called, okay, this divergence, okay, you have for small wavelengths, you have the UV catastrophe. Okay, why is it a catastrophe? Because you have a black body, okay, will have an infinite energy at this wavelength, okay, and so you know it is not physically, it's not reasonable, it's not physical, it's not observed. So this model of religions doesn't work. Okay. So do you have question? No question? Okay, so let's go on. Okay, to finish this part of the blackbody radiation, right? And so what is the explanation? Planck gave the explanation, the mathematical explanation, okay? So this is Planck's works, okay? So what you have here, okay? These are the experimental measurements, okay? And so what you have here as a first try to understand, okay, what happens, okay, and a first tentative of description of this blackbody radiation doesn't work, okay? So you have this UV catastrophe, okay? And so a lot of people were working on that at the time, okay? So you can see that it was religions, I think it was 1912, I think. No, it has to be sooner. Okay, because Einstein gave the explanation in 1905. Okay, so at the end, really, of the 19th century. Okay. Okay. And so, what is the explanation proposed by Planck? Okay, so this is a mathematical explanation at first. Mathematical explanation. Okay. So probably what he did was finding some function of lambda, okay, working, okay, for this observed curve, okay. So you have u of lambda, okay, working, adjusting, okay, the experimental curve. And so you see, we don't have a lot of freedom here to try to find a new explanation, because two things were supposed here to calculate u. It was the number, okay, of modes in the cavity, okay, and it was the mean energy of these modes, okay. And so some people try to work on this part to see if it was really this one. And classically, okay, we had this KT. It happens that what is different is u of lambda is really equal to n of lambda times e, okay? But this time, to adjust the experimental curve, we should have something that depends on lambda, okay? It cannot be a constant, because being a constant of the temperature, we saw that it leads to the UV catastrophe, okay? And so this is actually equal to 8 pi over lambda to the fourth, okay? But Planck observed, calculated, okay? So this was really a mathematical explanation, because he showed that if you say that the oscillators in the cavity, in the cavity wall, okay, in the cavity walls only oscillate at it's not the frequency you will. In packets depending. Okay, I will call it energy packets. Okay. Okay. Proportional to, so, okay. I will put proportional, okay. It's not F, it's nu, okay. The frequency or oscillation. Okay, so this will completely change this distribution of energy, okay? So you don't have any more, okay? Even if you say you have F of E proportional to exponential of minus E over KT, okay? So now you don't have E. Okay, you will use this one, okay? And so only the fact that you quantize, okay, the energy, you will have an effect which is, I will give the final result here, and we are going to analyze it, okay. Okay, the frequency of oscillation. So you will have, okay, so you will have E, okay, average, which will be now, you don't have a continuum, okay, of epsilon, okay, so you will have a sum, okay, of the energies, so you have E exponential of E minus N epsilon over KT, okay, and so you have N equal 0, okay, no energy to infinity, okay, and if you do that, you will find, I will put the result here, you will find the following, you will find this is equal to exponential of KT minus 1, okay, and so you know that epsilon is M. No, epsilon is not M, it is H nu, okay, over exponential of H nu over, this is H KT minus 1, so this is the Planck distribution. Okay, so actually this function, okay, this constant H, okay, that Planck, where is the constant H? Okay, here. Okay, attends. Epsilon. This is the first time actually that this constant was written, okay, because it was Planck who said it. And so when you have it, let's write now. Page. The density of energy, okay, as a function of lambda equal, the number is still 8 pi over lambda to the fourth, okay, times this Planck distribution, okay, so this is h nu over exponential of h nu over kt minus 1. Okay, so we have lambda. I will write it here. H c over lambda. Okay, no. This is c over lambda. Exponential of h c lambda kt minus 1. Okay, so we have this function of lambda. So you can see that we have two functions of lambda. Okay, we can say that this is this one, f1 of lambda, and this one, f2 of lambda. Okay, so this one we already saw that it is tends to 0 when lambda tends to infinity, and this one when what the problem is when lambda tends to infinity. Okay, so lambda tends to infinity. What do we have here? So this is exponential, or this is exponential. Lambda is really big, so this is very small. Okay, so we tend to 1. Okay, and so we have actually something what will be okay. Actually, we have to you have first an increasing, okay, this f2 of lambda increases, okay, from 0, okay, when lambda, sorry, this is 0 here, okay. So we have some divergence, and we have here also, okay. Okay, so this tend to 0, this tend to 0, because this is 1, this is 1, this is 0, 1. No, this is infinity. Là, vou compartilhar aqui. Esse tempo todo eu estava compartilhando, né?
Você em train de résister?
Não, compartilhando só. Não. Okay. So, just let me write it here. Okay. I'm going to do here, this lambda here, I will put it, okay, to the 5 HC okay, so well, this is a constant, okay, so we have f1 of lambda, and we have f2 of lambda. So this one, this is the Rayleigh jeans. No, it's 1 over lambda Rayleigh jeans. Okay, 8 pi over lambda 4. Okay, so we can see that when why do we avoid here the UV catastrophe? So when lambda is very small, okay, high frequencies, UV, high frequencies, UV catastrophe. Okay, here it diverges. UV catastrophe in Rayleigh jeans equation. Okay, so this one of Planck equation. Okay, this equation avoids this problem because you multiply by a function that depends on lambda as well. And so what does happen when lambda is very small? So lambda tend to 0. This goes to, this is very big, okay? So you have f2 of lambda, which is this one. So 0, so this is exponentially, this quantity tends to infinity, okay? And so you have something that tends to 0, okay? So you will have at this two functions, okay? This one, okay, diverges, and this one, okay. The fact is, okay, we can write it and do some approximations, and this term, okay, this function f2 of lambda salvages, okay, it really fits very well actually. So we can go back to this figure, and so you have these experimental points, okay. You have the Rayleigh jeans law, okay, which doesn't work, and you have the beautiful Planck's law, okay. And this is really working, and so from the adjustment, obviously it works if you adjust the value of the Planck constant, okay. And so if you adjusting Planck equation to experimental measurements, okay, experimental curve, you determine the value of the Planck constant, okay, h, okay, which is called the Planck constant. I think that now this constant also has an exact value. Let me see here. Yes, this is the basis of the measurement of the new kilogram, okay. So let me find I want to show you here the screen, okay. And so this one, we have this table of constant, and the Planck constant is exact, okay. So this is really a pillar of the modern physics, okay. So this is this value. I can't just take the value here. Okay, and the unit is obviously so second. Okay, so that when you have h times the frequency, okay, is an energy. Okay, because this is per second, this is hertz. Okay, so this is per hertz. Okay, and this is exact. So anytime we will have the opportunity later, okay, maybe to see the frontier between the realm of the quantum world and the classical world. Okay, quantum world particularly is the world of the small. Okay, the particles, okay, elementary particles, atoms, things like that. And so you only can describe them with the use of quantum mechanics. Okay, so we are beginning, okay, to see where it comes from. Okay, and you have the classical physics which work for a lot of macroscopic phenomena. Okay, and so there is always you always have to verify, okay, to check that your more complete theory, which is in this case this is a quantum theory, when you go to the for example bigger size, for example, things like that, we will see it when you go to the frontier. Okay, when you should find, okay, the limiting case of the classical world. Okay, and so you have classical expressions, and you have quantum expressions. Okay, representing the same phenomenon, but if it has h in it, it is the quantum one. Okay, you don't have any classical equation. Okay, with the Planck constant. Okay, Planck is a signature of quantum effects. Okay. Okay, so this is very nice. Planck found this beautiful result, and he really didn't understand it. Okay, this is what we say, and I believe he didn't, because who explained it later, okay, had a more fundamental explanation, description, was Einstein. Okay, so Planck solved the problem. So once you have this kind of Planck's law, okay, one application which is a very beautiful application. Okay, so maybe I can go to the book. Okay, so I have the book. Maybe let me stop here, and I will only okay. I want to show you something very, very, very beautiful. This is related to the relativity. Okay, this Big Bang theory. They said, okay, this is a theory which is still discussed. Okay, the Big Bang theory. All our universe comes from a very, very, very dense, okay, point, okay, in the space-time, okay, and you had some emission of light, okay, which, if you believe, okay, this theory, there must have been emission of light, okay, and after equilibrium, okay, thermal equilibrium was established. So you should have something which is in the universe, in the whole universe, which is quite homogeneous, okay, and some traces, okay, of this distribution of light, okay, in the primordial universe. And as the universe is getting colder, and it depends on the temperature, okay, so it should be possible to observe this. And actually this is, let me see, let me take here a figure of the book, okay, the Tipler. I will. Okay, so this is. I think here this is photoelectric effect. This is not the photoelectric effect. Okay, so let me show you something. Maybe you have already heard of that, okay? This is a figure of the Tipler. Okay? And so you have the energy density spectral distribution, what we called U of lambda, okay? Energy density, as a function of, here it's as a function of the frequency, okay? Nu, okay, I call it nu here, I call it F. You have lambda nu equal to C, okay? And so, as a function of the frequency, you have this measurement of the cosmic microwave background radiation. It was measured, I think, for the first time in 1965, okay? And it has been measured over and over again. It's quite homogeneous, okay, from all directions. In the universe, you can measure, okay, this energy, okay, per, okay, between, okay, this is at some frequency, electromagnetic frequency, and so it is really, okay, something, okay, you don't have any point, okay, outside the curve. You can adjust it exactly. So they say here that it was adjusted to a temperature of 2 point T equals 2.725 Kelvin, okay? So there is something, okay, here, certainly. And it was much hotter, okay, billions of years ago, okay? So the universe was hotter, and so the curve was like what? You have the maximum of the wavelength. It is not the maximum of the wavelength. This is nu m, okay? So you have, we saw that u of lambda varies as 1 over, no, not u, lambda m. Okay, 1 over t. And so we will have nu m varying as the temperature. It should, and really it should, when you increase the temperature, so it was at a value much higher, okay? So this is 10 to the 9th hertz. It's very, 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 very low frequency, okay? Gigahertz, sorry, gigahertz. Okay, I remember you that visible light, the frequencies are around 10 to the 14th, okay, hertz. So this is low frequency. Okay, so we don't have a lot of time. I wanted to, I don't know if I will have time. Okay, let's begin, okay, with the photoelectric effect. So, who explained it? Okay, this effect, okay, discovered by Planck, okay, without a lot of physical insight, okay, into the phenomena, okay, leading to this distribution, okay. So in 1905, okay, Einstein, this is the golden year of Einstein, so he wrote 3 papers, okay. So the Brownian motion. Okay, I spoke of it on in the last lecture. The restricted special relativity, and the photoelectric effect. Electric effect, okay, and he won the Nobel Prize for this one, okay, Nobel Prize for this discovery, okay, this explanation, okay. So it seems very okay. So photoelectric effect. Everybody uses photoelectric cell, okay, to do a lot of things, okay. With you can put one. What is the principle? First one, it was observed by Hertz. Is 87, I think, when Hertz verified, okay, that light and electromagnetic waves, okay. Light is an electromagnetic wave, okay. And so doing that, he observed, okay, some phenomenon, actually he discovered, okay, the photoelectric effect. So how is it? You have some, this is not the Hertz arrangement, okay, because you have no electric circuit. Hertz, he had two, it had a circuit, okay, an oscillating circuit, okay. He could tune, okay, the frequency of the oscillation, and he emitted some light, okay, through a spark, okay, and he showed that this and this was clearly electromagnetical, okay, because you had you applied the law of Maxwell, okay, to the circuits, to electric field, magnetic field, and so he showed that light was an electromagnetic field. This is another arrangement, okay. This is something to study, really, the electromagnetic field. So you have some evacuated, okay. You have a pump. The pump is supposed to lower the pressure, okay. You don't want to have collisions, okay, of your electrons, okay. You are going to study cathode rays, okay, with this one, and you don't want to be disturbed or to have some other effects, okay, occurring because of collision of atoms, of electrons with some residual gas here in the chamber, okay. And so you have the cathode and you have the anode, okay, and so they are I won't put it here as initially this is the plus and this is the minus, okay, and actually this is the minus and this is the plus, and you accelerate, okay, the electrons, okay, between the here really you will change this sign. And so in the cathode ray we studied on last week, we had a high tension, okay, between the cathode and the anode, and actually what we can have, so this is a surface, okay, which is the cathode, and you can observe that if you illuminate this cathode with light, okay, you will have emission of cathode ray, which you now know are electrons, okay. So you are going to emit the surface is emitting electron because it uses the energy of the light, okay, to have electrons. Arrancar. In Portuguese, I don't remember in English how we say that. And so you can study, okay, this effect of the light on the cathode by varying. What can you? So this is light, and so light has what? An intensity, okay. Intensity is energy, okay. Energy per second per square meter. Okay, this is intensity, but particularly this is power. Okay, you can vary the frequency. Okay, the wavelength of the light, the frequency of the light. You can vary, well, the light, this is essentially what you can vary. Here, what you can vary, you can play with the tension. It can be positive, it can be negative, okay? And so what you are doing here, some of the electrons eventually accelerated or not, okay? They are emitted by the surface, and some of them will reach, okay, this part here of the chamber, where you have they will be measured as a current, okay, E, which will be the current. Maybe E, I will use it for intensity, and I will use E, okay, lowercase e for current, electronic current, okay. And so this is what you observe. This is very easy, okay. I will first show you what you observe, okay, as a function. So you write, okay, you measure, for example, this current. This is what you measure, actually, okay. This is what you measure, the current, okay, and you measure it as a function of these things, okay. So you measure it as a function of V, okay, difference of potential between the electrodes. You measure it as a function of intensity, you measure it as a function of frequency. So first we will begin with as a function of the intensity and V also, okay. So you have on the horizontal axis you have V, okay, which is the tension between the electrodes, and so it can be negative and it can be positive. What does it mean when it is negative? This means that this one is more positive actually than this one, okay. And so what happens is that your electrons, which you know are have a negative charge, okay. So if it is a negative V, what will happen is that they will be slowed, okay, by the interaction, okay. You have what is the acceleration, okay. I will write it. Acceleration, you have a force, okay. So between the cathode and the anode, for example, okay, you have a force, okay, you have an electric field, okay, E, okay, which has it is like this, okay. If V is positive and it is no, actually if V is negative and it is like this if V is positive, okay. And so the force on the electron will be F is equal to the charge of the electron times, okay, the and actually it is like this, okay, and E is negative, okay. So I can write it here also as minus, okay. And so let's see, and the acceleration, is it sufficient to, yes, okay. So this is if V is negative, okay, the electrons, the acceleration, okay, I need it, equal m of the electron, okay, times the acceleration, okay, t2, let's say this is x, okay, axis, d2x over dt2, okay. And so if V is negative, and so E, negative, you have E like that, so you will have d2x over dt2, okay, which will be negative. Okay, so the velocity of the electrons, okay, will decrease, okay? They are emitted and the velocity is decreased. Oh, I will have to stop here, okay? Because really, this is only the first part of the thing, and so after that we have also the problem of the frequency, okay, and after that we have Compton effect, okay. And so the Compton effect, actually, I didn't want to do it, to see it today, because I would like to do it together with the end of special relativity that we didn't do in the classroom. And I promised, and I will do it, okay, that I would speak a little about the energy part of the relativity, and the Compton effect. We will see it uses, okay, this part, because it treats the electron, okay, as a particle which has a linear momentum, okay, and it is relativistic. It is very, very high, and so we have to treat it relativistically. The electron, no, yeah. Sorry. Well, the photon, sorry, okay? We are talking of quantization of light, okay? The photon is a relativistic particle, okay? And so we have to use the relativistic relation. Okay, so I will do it. Okay, I will send today, the two videos. I think I didn't send the other one, and this one, and a list of exercises of problems, okay, homework on quantization of charge and quantization of light up to now, okay, so about the blackbody radiation, okay, and so